Good morning, everybody. Today we will continue our discussion about medical statistics. This part of our education, of your education of our studying is a long part, and today we will continue. It will be second part, and today we will look at quantitative data analysis. So, in previous lecture, I told you about the importance of checking the normality of the distribution. Why? Because in further analysis of the data, depending on the type of distribution, what type of distribution, normal distribution or not normal distribution law, there will be a different algorithm for describing the data and analyzing it. Firstly, we must know what type of distribution there is in our sample. Only after that we can choose the method of analysis of our samples. So, and we begin our analysis of quantitative data by testing the hypothesis that the distribution is normal. So, we can see that if our hypothesis is confirmed, we can say we accepted the null hypothesis. Then what is it? What is next? Then we describe our data by its average value and indicate the 95% confidence interval in parentheses. So you can also add a plus minus standard deviation to the average. This is also done. We can do it, and I think I recommend to you to do it because it in your scientists or scientific analysts, you can show other people, you can show other scientists your real data, your real interval, where you can show us your results of your test, for example. So, and then what is next? Depending on the number of groups, after that, after confidence interval and average value, what happened? We must see how much samples is in our test, for example. So, how much groups, for example, we have, or how much samples is. So, we look for the difference between the groups using the following criteria. If we are comparing two groups of quantitative data, I say again, today we will talk about only quantitative data analysis. So, if we are comparing two groups of quantitative data, we use students' t-tests for independent samples. If they are independent, we must remember, we must not forget about it, that we must analyze samples using simple statistics methods, and in this analysis we must remember, we must see what type of samples we have, independent or dependent, because from this the criteria will be different, which we can use in our next analysis. So if we have independent samples, we must use students' t-test for independent samples. But if our samples are dependent, we should use paired student t-test and slightly different. And if we are comparing more than three groups, it may be, then if there is a normal distribution law in samples, we have to use a one-factor analysis of variance and then posterior comparisons of each group to each other. There are some subtitles there. We need to introduce correction for multiple comparisons, because if we have many comparison groups, the probability of error can accumulate. But yeah, this is not part of our course, and if we have more than 3 samples, we will not educate, we will not study this part, because this is a complicated part and you will talk about it later, yeah, in your elder courses. So in our course, we will talk only about when we have 2 samples, 2 different groups. For example, it may be dependent or independent. So, in our course again, we will only be looking at students' test for dependent and for independent samples. So, if we rejected the null hypothesis, so we can say that a null hypothesis is not accepted, and what happened? Normal distribution law of our data is not satisfied here in our samples, and so then we must describe our quantitative data using the median and interquartile range and quartiles. So, and after that, we must see again how much samples, how much groups we have. After that, we compare our samples again. So, if we are comparing 2 groups, 2 samples, what happened? We first need to know with you whether these samples are dependent or not dependent. Again, yeah, independent samples or dependent samples. So, if our 2 samples are independent, we will use the Mann-Whitney test for analysis. But if our samples are dependent, we will use the Wilcoxon test, or other names. You can see paired T criterion, or also people can call the Wilcoxon T criterion for comparison. Yeah, it's all names of this criterion is right. So, but these criteria we use only when we have 2 samples. But what happened if we have 3 samples? So, if we have 3 or maybe more groups to analyze, more samples to analyze, we will use Kruskal-Wallis criterion, and then after this criterion we must use posterior multiple comparisons, and we must not forget to introduce corrections to many numbers of samples. And again, multiple comparisons are not part of our first year medical statistics course in our department. We will talk only when we have 2 groups, dependent and independent samples, when the normal distribution law is accepted, here is our null hypothesis is accepted, or if we did not accept the null hypothesis, and we can say the normal distribution law is not here in our groups, in our samples, so we can use Mann-Whitney test or Wilcoxon test when we have independent or dependent samples. So, and now we are faced with the question, how do we test this hypothesis of distribution normality? The null hypothesis we have is that the random variable x obeys the normal distribution law, and the alternative hypothesis is the opposite. Then that the distribution of the random variable x is different from the normal distribution. And again, I can say you again, a different from normal distribution does not mean that it's not non-normal or paranormal distribution. Yeah, we can say. No. It's simply a different distribution, and we will use different methods to compare our data. So, The hypothesis of a normal distribution is tested using the following criteria, depending on how many items in your samples. So before we said how much samples we have, yeah? 2 samples or 3 samples and more maybe. And after that, if we have 2 samples, after that we must see how much items in our group, in our samples. So you can use Pearson's square criterion, Shapiro-Wilk criterion, and Kolmogorov-Smirnov criterion. The conditions for the applications are written on the slide. Yeah, currently, Shapiro-Wilk criterion is most commonly used for samples of less than 50 items, and if there are more than 50 items, the Kolmogorov-Smirnov test is used. Yeah. There are also other ways to assume normality, but still the criteria are more reliable. And in our first year program in our department, you and I will talk about Shapiro-Wilk criterion and usually use it to check it in our practical classes, yeah, in our estimated works. But also in your manuals, there is Pearson square criterion, and some teachers additionally ask you to use it to check normality of distribution in samples or not. So let's continue. And on the lecture, we will only use and we will only talk about Shapiro-Wilk criterion. And there is the algorithm for hypothesis testing, yeah? And what is the algorithm of this criterion? Firstly, it's absolutely standard, as I told you in last lecture. Firstly, we have to make hypothesis. After that, we begin our test by calculating the statistic of the criterion. And in this case, it's calculated using following formula, and that you can see on the slide now, upper formula. So, what is about n? N is the number of items, yeah, in our sample, or we can say sample size. What is about d? D is the sampling variance in our sample. And what is about b? B is the number that is calculated as follows. Yeah, you can see the special formula about B. What is about B? And you have formula to below on the slide. And what is this? In this formula, what is about alpha and k? Alpha and k is auxiliary coefficient. We look them up in tables, in special tables, and in your tutorial you are listed at the very end. Yeah? At the end of your book, you can see these special tables for different criteria and use and choose, yeah, the coefficient alpha from these tables. So, what is this? This is the value that depends on the sample size. Then the value that is in parentheses. So this is the value that we get with you as a result of calculating the criterion table. First, we order our sample. Yeah? Then look, we have x n minus k plus 1 minus xk. For example, if k is 1, then the value is parenthesis is k is 1. So n minus 1 plus 1 is n, will be xn minus x1. That is, we subtract the first from the last element of our ordered sample. Further, if k will be 2, then we have xn minus 1 minus x2. This means that we subtract the second element from the penultimate element of our ordered sample. And for example, if after that, then if k is 3, we get xn minus 2 minus x3. That is, from the third element from the end of ordered sample, we subtract the third element first, and so on, so on, so on. For example, we come to see the numbers. So we converge to the center of the sample. For example, if I draw the table for you, for example, we have ordered values, many ordered values. And for example, 1, 3, 5, and the last is 8, maybe 0, 2. For example, what happened? First minus last will be number. Second minus second from the end, 2 minus 0, for example, will be 2. Third, 3 minus 2 will be, minus 2 will be 1, for example, the third element from the end is 2. And, for example, we come together, and come to the center of the sample. After that, we have the numbers, difference between these numbers. What is the next? Then we multiply our sum of these elements by our alpha coefficient and get our number b. We must multiply this difference by alpha and take the sum of this column in the table. And what happened? In this way, we calculate the benchmark value of the criterion. Next, we compare the control value to the critical value for a given number of elements in the sample. If the control value is greater than the critical value, then we have no reason to reject the null hypothesis. And this means that the sample fulfills a normal distribution law. And if the control value of the criterion is less than the critical value, then the null hypothesis is rejected. This means that the sample does not fulfill the normal distribution law. You can see this part in the second part of our algorithm. We must compare our control value, which we calculated according our sample, and with critical value. Compare it with critical value. Critical value we find in special tables according our sample size, and compare it. And after that we can say no reason to reject the null hypothesis and normal distribution law is satisfied, or opposite, null hypothesis is rejected, so the normal distribution law is not satisfied, for example. So let's look at an example. We have a sample of presumptive fetal weight values that we found out using ultrasound diagnostic. We have a sample of 42 items, 42 items, the sample of estimated fetal weight. 42 numbers, 42 items in our sample. Our task is to test the hypothesis that the distribution law is normal. Using the formula on the previous slide, using this formula, this part, I performed the calculation, and we will look at how to perform the calculations in detail in the practical exercises. In this case, it turned out that the criterion control value, we can see control value in our criterion is 0.959. It detailed calculation in the practical exercises. Next, use the table of critical values of the Shapiro-Wilk criterion for the sample size of 42 numbers, because we have 42 items in our sample. So it turns out that the critical value of the criterion at the significance level of 0.05 for a sample size of 42 items was 0.942, and for a significance level of 0.01, the critical value of Shapiro-Wilk criterion is 0.922. So, this chart shows these values and the area of insignificance. We talked about it in the last lecture. It turns out that our control value lies in the region of insignificance because our control value is more than our critical values, yeah, for both of level of significance, yeah. And so the insignificance of differences from the null hypothesis. Accordingly, we can say that with a 95 confidence level, the null hypothesis is accepted and the normal distribution law in the sample is satisfied. Is satisfied in this example, for example. So if we draw the histogram for the same case, for this case about estimated fetal weight, where we have 42 items in our sample, and you will also draw the histograms in your practical classes, yeah, when you will calculate the estimated works. After that, we can plot the normal distribution according to these conditions. Then we will see that our distribution is very close to normal distribution, you can see, yeah? So, based on the histogram, only on this histogram, we can also suggest whether the normal distribution law is fulfilled or not. But this is just an assumption and it can be wrong, really. For histogram, we can only think, and then really this is normal distribution law, or maybe not. But how can we prove it? We must use the criterion to calculate and prove it after calculation. Only calculation, only special criterion can answer on question. Normal distribution law can be or cannot be in our sample, for example. How you can see on this example about estimated fetal weight. We tested the null hypothesis about normal distribution, and as in our example, it turns out that the distribution is normal. Yeah, we proved it. So, what is the next? What do we do next after this? If the samples are independent, we use the t-test for independent samples. After that, this criterion was published in 1908 by William Gossett. But why is the criterion called student test? Other name of this criteria is student t-test or t-test. Yeah. At the time, Gossett was working at the Guinness Brewery. So he was working on evaluating beer quality, breeding the highest yielding variety of berry, and he couldn't use his name to publish his statistical work because he had a contract with the brewery that stated that all data which he came out of the brewery was a trade secret. And he used his statistical analysis from his work, yeah. And so he published his work under the pseudonym Stewart, yeah, Stewart. This pseudonym is well known in statistics, and this criterion is very popular to these days, and more than one. And what is about this test? This t-test for independent samples. In this case, the null hypothesis is formulated as follows. The mathematical expectation of sample x1 is equal to the mathematical expectation x2. You can see this is a null hypothesis. Again, the mathematical expectation of x1 is equal to the mathematical expectation x2. The alternative hypothesis is opposite, that the mathematical expectation of x1 are not equal, or mathematical expectations about x1 and x2 is not equal, and they differ significantly. Otherwise, we can say that the mean value or average value in the populations are different. And what should be the conditions of application? Firstly, the normal distribution of the data is mandatory, because we can apply this criterion only if the data are distributed according to the normal distribution law. And that is, we must check our samples for normality of distribution. It's also very important that this criterion is applicable only when the conditions of homogeneity of variances is met, and that is when the variances are approximately the same, or equality of the sample variance and normal distribution law of our data. There is a correction for this criterion when the variances are not equal. It's called Yates correction. And it's implemented in statistical software packages, and we don't study it in our course too. In our case, to apply this criterion, we need a normal distribution in samples and homogeneity or equality of variances. So the algorithm is the same as before. What was the before, in our example before? So we calculate the control value of the criterion, calculation of the criterion statistics. This is a formula on the slide, you can see, and I think it seems very scary and at first glance, but it's not really. It's very simple formula. So in the numerator, we have the difference of the mean value modulus. N1, what is about N1? N1 is the number of elements in the first sample. N2 is the number of elements in the second sample. This is the difference between average values, D1, what is this? Is the variance, sample variance of the first sample. And D2 is the sample variance of the second sample. The same numbers, N1 and N2, this is the numbers of first and second sample. So, the number of degrees of freedom is an important notion on which critical values of the criterion we depend, which we look for in the tables. It's calculated as the sum of number of elements of both sample minus 2. This is number of degrees of freedom. So, for example, we calculated T control for our sample. What is the next? After we have calculated the criterion statistic, we have to see where it's on our axis, like before example was. So we look at the critical values from the table, they depend on, how I said, they depend on the sample size and the number of degrees of freedom. It turns out that if the control value is less than the critical value on the left side for the chart, then we accept null hypothesis and say that the sample mean values don't differ significantly, or average values don't differ significantly. That is, the groups don't differ very much. But if we have a control value greater than the critical value, then we say that the sample mean values or average values differ statistically significantly with a 95% confidence probability, and if the value lies in the middle interval in this interval in the diagram. And with a 99% confidence probability if the value lies in the area on the right. So often you may encounter words when they say that the differences between the two groups are persistent. You can't say that, because a credible event is an event that happened with 100% probability. We talked about this with you in our probability theory lecture. We can't have values with 100% probability in principle, because we are making a generalization to the entire population based on the sample. So all of our conclusions come with some probability, maybe 95% or 99%. We are not saying differences are persistent. We must say differences are statistically significant. Yeah, really, statistically significant. Don't forget about this name. So, let's break down with you an example of how the T criterion is calculated. Yeah, this was theoretical information, now practice information. How can we use and how can it work, or how can we calculate this criterion? So we have two small groups, and the sample of patients with irritable bowel syndrome in which diarrhea appears is 15 people. They also have a mean serotonin count, 134.0 nanogram per milliliter. So, if 95% confidence interval and standard deviation is given, confidence interval, standard deviation. Confidence interval, standard deviation, sigma. We went over how to calculate all this in the last lecture. It's simple statistics, and we won't repeat it here really. The second group is a sample of patients with irritable bowel syndrome with constipation. There are 11 people in this sample. Again, they also have the mean serotonin value calculated, the 95% confidence interval, and the standard deviation too. Serotonin number, confidence interval, and standard deviation. And for example, we can compare these numbers, and we see that the standard deviations are about the same, near numbers, which means that the variances are about equal. But notice that the sample averages are different at first glance. The values in the first sample are higher, let's see. But if we look at the confidence interval, we see that they overlap each other, For example, right part is overlapped to left part, of group 1. So, there is an overlap in the interval, so we can assume that most likely the sample mean values differ quite a lot at first glance. But given overlap in the confidence intervals means that the most likely the difference will not be significant. And let's check it. If we substitute our values 134 minus 113 in the numerator, the sample first size is 15. sample variance is, oh, no sample variance, sorry, yes, sample variance, sorry. Sample variance of the first group is 38.7, and we must put it in square, yeah? And for example, about second group, the sample size of second group is 11, yeah? And sample variance is 33.4 in square, yeah? In square. So, into the formula for calculating the criteria, we should put these numbers in this big formula. And let's calculate the fraction. We get, after that, we approximately have 1.4 after we put all numbers here in this big formula. So, the number of degrees of freedom is 24. After that, proceeding from the number of degrees of freedom, we find the critical values according to the students' distribution tables. And we can see. And after that, we should put it on our line. On our line. So, 2.06. This is a critical value for significance level of 0.05. And 2.8 is for a significance level of 0.01. We see that our control criterion value of 1.4, which we calculated according to this formula, is less than the critical value for significance level of 0.05 and 0.01. And what does it mean? Which means that it lies in the region of insignificance or area of insignificance, this area. Thus, since the differences are insignificant, we accept the null hypothesis and can say that with a 95% confidence level, the sample means differ insignificantly, as we first hypothesized from the overlap of the confidence intervals. So, this is how can be calculated t-test for independent samples, yeah, for independent samples. And we must not forget about special conditions when we can use or when we can apply the t-test for independent samples, yeah. And one of the conditions for applying this t-test was the condition of homogeneity of the variances. And the null hypothesis is that the mathematical expectations of the variances are equal, because we can take many samples from the population that have their own variance. Our condition means that the mean values of the variances are equal. The alternative hypothesis, yeah, the first null hypothesis and alternative hypothesis, the inverse in this case. And it says that the variances are not equal. We can test homogeneity of variances using the special test. We can the tests may be Fisher's or Legends test. In our program, we consider Fisher's criterion. It's probably simplest. So, the simplest, yeah? And we have calculated for each sample the variance, and then to calculate Fisher's criterion, we divide the larger variance by the smaller variance. And the number of degrees of freedom in this case is n minus 1, you can see this part. And then, after that, we compare our benchmark value with the critical values from the Fisher's distribution table. And for the number of degrees of freedom A, it's n minus 1, yeah? We look for the critical value for the significance level of 0.05 and 0.01. Again, if our value lies in the region of insignificance in this part, yeah, area of insignificance or region of insignificance, the left part, yeah, we accept the null hypothesis and can say that the variances are approximately the same. But if the control value lies in the mean interval in this part, more than 0, 0, 0, more than this part, less than this part, we can say that the variances differ statistically significantly with 95% confidence level. But if the control value lies in the right-hand interval, significant level, yeah, area of significance area, we can say that the variances are statistically significantly different with a 99% confidence level. And in practice, you will test the homogeneity of the variances using this Fisher's criterion. And after that, you must write the conclusions here of this criterion. So, in the case, we have dependent samples. The task is reduced to comparing the new value x1 minus x2 with 0, yeah, with 0, that value. Previously, there were sample x1, sample x2, and we compared them to each other. But what happened in this situation? In this situation, we have paired values. For example, maybe situation that the first sample is before the procedure and the second sample is after the procedure. And it turns out that we have the same patients before and after procedure, or the same patients who took one drug and after that took another drug, they are at different time. The patients are the same. Be careful. Paired values say us that the patients are the same. And in this situation, we must create the new value as a difference of the before and after values. So the null hypothesis would be that the expectation of the new random variable is 0. So, the control values will be calculated using the formula on the slide. You can use it according to this formula on the slide, where that with a dash, yeah, is the modulus of what? Differences between average values, yeah. What is about zi? This part, zi. That I is the difference between the elements of the first and the second sample, you can see. The number of degrees of freedom in this case will be n minus 1. So, by the same scheme, we compare with the critical values. Yeah, after that, and what is the next? Yeah, let's look this example according this paired t-test. As in your first calculation in the practical exercises, we have two samples of cardio interval data or values before and after drug administration, for example. We need to test the hypothesis that the differences between the samples are significant. And what should we do? In the table on the slide, you can see the table on the slide, and in this table on the slide, in column 1, you can see the first sample. Column 2 is about second sample, numbers from second sample. We count the T1 minus T2 differences, these differences. Yeah, according our formula, yeah, you can see. So then we square those differences. Yeah, we put in square these differences and write it numbers in the fourth column or in the last column. And in the last column we have of the sum of the table. Yeah, we must also calculate the sum of all elements of last column. We should summarize last column and put the sum of this. Yeah, so we substitute this sum in the formula, and we also take the sum of z squares. Yeah, we get the sum of squares minus the square of the sum in the denominator under the root. Z with dash is the difference between the average values. Yeah, we talked about it. The sample mean in the first sample is 0.8 minus the sample mean in the second sample 0.65, and answer will get 0.15. Substituting all of our data into the formula for calculating the criterions control value, yeah, according to this big formula, we take answer 5.157. And the number of degrees of freedom in this example is 10 minus 1. We said n minus 1 is 10 minus 1 is 9. According to students' distribution tables for the number of degrees of freedom of 9 for the significance level of 0.05, the critical value of the criterion is 2.26, and for number of degrees of freedom of 9 and the significance level of 0.01, the critical value of the criterion will be 3.25. We plot them on the axis again, and our control value is greater, 5.157 is greater than these critical values. And therefore, we can reject the null hypothesis with 99% confidence interval and say that with 99% confidence, the differences in the cardio intervals before and after the procedure is statistically significant. And that is, the new random variable z, value difference, is statistically significantly different from 0. Differs from 0, and differs significantly, we can say. So, we looked at the T criterion for independent sample Cs and paired T criterion. They can work only in the case of normal distribution in the samples, how I said earlier. And if the distribution law is not normal, non-normal distribution law, we must use non-parametric criteria, which are naturally less powerful, but they allow us to work with distributions other than normal. If the samples are independent, we use the Mann-Whitney U-test, also called the Wilcoxon-Mann-Whitney test, and to test for difference between those samples. It was originally created by Wilcoxon, but Mann and Whitney improved it quite a bit, and so it's now called the Mann-Whitney or Mann-Whitney U criterion. And what is about null hypothesis? The null hypothesis here is formulated as follows. The distribution of the sign in the first sample corresponds to the distribution of the sign in second sample. So, in fact, it says that the samples don't differ from each other. So, there are no differences between the samples. But how does this criterion work? Let us consider the algorithm of the criterion. What is the first of this? Firstly, we must make a single ranked series of both samples. We unit the samples together, make a single sample, arranging their element by the degree of growth of the attribute from the minimum to the maximum. Then we put ranks, where a smaller value corresponds to a smaller rank. If there are repeating elements, then we take the arithmetic average of these ranks, the average rank, we can say. Then we count the sum of ranks which fall on the first sample and the sum of ranks which fall on the elements of the second sample. Then count the U1 and U2 values using the following formulas. You can see it on the slide here and here. And what is about N1, N1 and N2 are the volume of the first and second sample, respectively, and R1 and R2. And what is about R1? R1 is the sum of the ranks of the first sample, and R2 is the sum of the ranks of the second sample. So, next, what is the next? After this, we determine the control value of the Mann-Whitney U statistics. This is simply the minimum value between U1 and U2. Then we compare the control value to the critical value. And in this situation, we have two options. If the sample is smaller than 20 elements, then we look up the critical value using the Mann-Whitney critical value table. If it turns out that control value is greater than the critical value, we accept the null hypothesis. But if the sample is large, we may have more than 20 elements, we consider the control value Z according to the formula on the slide. Here you can see. Where U control is what we counted the smallest value from U1 and U2, and what is about N1 and N2, and these are sample volumes. We count the value of the criterion and then use the students' tables to analyze this value. And because this value is distributed according to the students' distribution for the number of degrees of freedom, N1 plus N2 minus 2. Then we proceed in the same way as we did when considering students' criteria. Then consider students' criteria. Let's take this criterion as an example. The new concepts of ranking are better examined with examples. It's really more comfortable for students to see ranks in examples. So let's consider with you the anxiety score in people with irritable bowel syndrome, IBS, irritable bowel syndrome. Again, we have two independent groups: irritable bowel syndrome with diarrhea and irritable bowel syndrome with constipation. You can see with diarrhea and with constipation. So these groups are independent, and these are different people. Small samples are presented to make it easier to give you an example. We have 7 items in the first group, you can see 7 items, and 8 items in the second group, for a total of 15 items. 7 plus 8 is 15. The bars show the anxiety index, the values of which were obtained with the help of physiological tests. You can see only numbers which doctors took from physiological special neurological test, physiological test, and gave it for us to compare, to analyze numbers. So you can see these numbers. So then note, we make a general sample, conditionally dividing them in order to make it clear to which sample in the item belongs. As a result, we distribute these values from minimum to maximum order, in order. This can be seen in the middle column, yeah, you can see, of the table, where we have arranged the values according to which sample the item belongs to and in ascending order from the minimum to the maximum value. You can see, yeah, we put this number and this number from the minimum to the maximum, yeah, and wrote numbers according the sample, first or second, first and second, first and second. So now we need to assign ranks. What is about rank? Rank is just an ordinal number, and there are 15 of them. So look at the first value, 39. The first value is 39, has rank is 1, because the rank is just ordinary number. Yeah, this is the first number. After that, next value is 40 and has ranks 2. Has rank 2. Then we have rank 3 and rank 4 for the elements from the second sample. Yeah, from the first and second sample. After that, we have repeating elements, you can see, 47 and 47. And their ordinal numbers are 5 and 6. But what is about the rank? The rank of these numbers is, how I said, is the arithmetic mean of the ordinal number. So we should put 5 plus 6. 5 plus 6 divided by 2 will be 5.5 by 5.5. And this means that the values of 47 and 47 will have a same rank of 5.5. Then the ordinal number 7 to number 49, yeah, we have rank 7. This number has rank 7. Ordinal number 8 for the number 52 is rank 8. Next, rank 9. After that, we have again the same values, 58, 58, and ordinal numbers 10 and 19. Yeah, you can see 10 and 19. And they are the same, which means that the rank will be the arithmetic average in equal to 10.5. Yeah, because 10 plus 11 divided by 2 will be 10.5 and 10.5 rank for each of the values. Yeah, 48, 85, 58, 58 and 58. Sorry. So then the ordinal number is 12, 13, 14 and 15. We have rank our total sample. What is the next? Next, let's consider that 35.5 is the sum of ranks from the first sample. We should summarize these ranks, and after that, and it will be R1 for the first sample, yeah, and summarize this summarize ranks of second sample, and number will be 84.5. It will be R2. After that, we should use the formula to calculate what? To calculate the value of U1 and U2, and the values will be 48.5 for U1 and U2 is 7.5. 7.5. Then our control value is lowest value of these two, which is 7.5, and we should choose 7.5 number. And since there are less than 20 elements in the sample, so we analyze by the critical value in the table. For a significance level of 0.05, critical value will be 10. And for a significance level 0.01, the critical value will be 6. Our control value is 7.5. We calculated it and choose the less number from this. So we plot our axis and mark our values here, and the value of 7.5 less than critical value for significance level of 0.05, but more than critical value for significance level of 0.01. And we already unambiguously reject the null hypothesis. It turns out that with 95 confidence level, we can say that the anxiety level of irritable bowel syndrome patients with constipation is statistically significantly different from the anxiety level of irritable bowel syndrome patients with diarrhea. This is how the criterion works. And we calculated the value of U1 and U2, choose the lowest of them, and compared it with the table values, and after that say reject the null hypothesis in our example. So it was independent samples, but if we have dependent samples, what happened? If we have dependent samples, we have to use the Wilcoxon-T criterion. In your calculation work, in your estimated work on practice, the samples are dependent before and after procedure or before and after different drugs. Yeah? So we need to use these criteria. The Wilcoxon criterion is non-parametric counterpart of the paired student test. The null hypothesis is formulated as follows: that the median difference in the population is 0. What is about alternative hypothesis? That the median of the difference in the populations is not equal to 0. So let's start with the algorithm and then look at an example. What is the procedure for working with the criterion? And the first thing we have to do is calculate the amount of change in the trait. That is, we find the difference between the values of the first and the second sample. Then we order them by absolute value. You can see the algorithm. Yeah, firstly calculated the magnitude of the change in the trait. So next is order the change by absolute value without taking into account the sign here and rank them. Then we add up the ranks of positive differences and the ranks of negative differences. You can see the third step. The fourth step is what? The criterion statistics will be the minimum of this sum. Yeah, don't forget about the third steps. Yeah, we compare this criterion criterion statistic to the critical value, and if the control value is less than the critical value, for example, if the control value is more than the critical value, there is no reason to reject the null hypothesis. So we can say we accept the null hypothesis. And let's again take the calculation of this criterion as an example to most understanding to you. So we don't have a large sample for convenience. It's more comfortable to me and to you to understand, and to me to show it in the slide. So we have a sample of 12 people who were given dietary recommendations. And let's test the hypothesis of weight loss after 6 months. Let's look at the first table. Let's start from the first table and let's look at the first table. We have body weight before the dietary recommendations and body weight after 6 months of dietary recommendations. We find the difference by subtracting what was before from what was after. What do we have as a result? That's the third line of the table 1. This is. Somewhere we got negative values. Somewhere you can see we got positive values. And somewhere we got 0. You can see here and here and here, maybe 0, yeah? Now we order this difference from minimum to maximum, but without the minus or plus sign. And after that, we should rank them. We don't take into account the 0 difference. We have 3 such values. You can see. Firstly, we arranged this number from the minimum to the maximum without minus here. We can't see, we must not see on the minus, on the sign here, only from the minimum to maximum. And we have 3 numbers which are 0. And we don't take into account the 0 differences. We must start from here. And we have 3 such values and put them in the beginning and don't take into account, yeah? It's not for us. It's not interesting for us. We again give them a number so as not to get confused. We got 9 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we have 9 numbers. Our sample is 9. Our sample has a volume 9. So, and then we must put ranks to our numbers. It turns out first are firstly. You can see this now. What is about number is ordinary, yeah? Only the number. First number, second number, third number, and other. Arranged is our sample, and we must put the ranks. Firstly, we have 2 numbers, 1 and 1. Don't see on the minus sign. The same numbers, and as usually, as we did it earlier, what is about rank? We must put the rank as the average value between the number, yeah, between the ordinal number. So what is will be 1 plus 2, because 1 and 1 is first and second numbers, divided by 2 will be 1.5. So the rank of these numbers will be 1.5 and 1.5. So next, let's see again. We have the same numbers, 2 and 2. And they have a number third and fourth, yeah, numbers in our sample. What is about rank for these numbers? Again, students, again, we have an average rank is average between number, the third and the fourth number. So 3 plus 4 divided by 2 will be 3.5. And 3.5 is the same rank for this and this number put in the table. So what is the next? Then ordinal number is 5 and have rank 5. 6 number, ordinal number 6, have rank 6. And after that, let's see. Again, the same number 7 and 7. And the ordinal number 7 and 8. What happened? Again, rank is the average value between ordinal numbers. So 7 plus 8 divided by 2 will be 7.5. 7.5, the same ranks for these values And the last value 8 has rank 9 because ordinal number is 9. We have ranked these values, yeah? And now we should compare. Now we should add up the ranks of positive values. They are highlighted in yellow. And the ranks of negative values is green, yellow, green, highlighted as green, yeah? So let's see, let's summarize, let's add up positive ranks of positive values and ranks of negative values. Let's start from positive, yellow color. Rank is 1.5, 3.5, and 5. So let's summarize it, and will be 10 of ranks of positive, yeah? Positive ranks. What is about negative ranks? 1.5 plus 3.5 plus 6 plus 7.5, again 7.5 and 9. It will be equal 35 about negative, yeah? The sum of negative ranks. So we choose the lowest value, so the control value is 10. We must choose the lowest value from these numbers, 10 and 35. Yeah, really, 10 is less than 35, so 10 will be control value for this, for our analysis, for our calculation of this Wilcoxon test. So, according to the paired Wilcoxon criterion tables, we look at the critical values, yeah? And the new number of sample items is 9. I said it because we have zero, we must forget about zeros, yeah? So, we get that t at the 0.1 significance level is 3, and t at the 0.05 significance level is 8. We should compare our control number with these critical numbers on different significance levels. So our control value 10, and 10 is more than this, both of these numbers, and this number and this number. So it lies in the area to the left, to this area, and which is the area of insignificance. So we accept the null hypothesis, how we said earlier. If our control number is more than critical, this is no reason to reject. We must accept the hypothesis. So we can conclude that there was no statistically significant change in body weight. I think you ask me why, what happened, because people have a 6-month diet recommendations, and what happened, student? The reasons for this are no longer clear to us. Yeah, it could be that people didn't follow these recommendations correctly, or the recommendations were wrong and not comfortable maybe for people, yeah, and for human, and this human thinker, I don't use this recommendation in my diet, for example. So maybe different conditions, yeah, and nevertheless, based on the experiment, it turned out that there was no statistically significant change in body weight, because we accept the null hypothesis, and there was no statistically significant change in body weight before the before diet and after 6-month diet, yeah, recommendations. So it may be really, students, and it's not connects with mathematical parts, for example. We have no mistakes, maybe it can connect with different conditions, and may be doctor's mistake, or maybe patient's mistake, really. So we are done with the quantitative data analysis. And I will give you again on the slide an expanded scheme of the algorithm of our actions. Firstly, what should we do? We should test the hypothesis that the distribution normal using the following criteria. For example, then, if we have a normal distribution law, what happened? We present our quantitative data in the form of the mean value and the 95% confidence interval plus minus the standard deviation, yeah? And after that, we can use the graph. And how? We usually present a graph with column of error. This is a graph of the mean value at the confidence interval. What is the next? Then, depending on the number of group, how I said, we should analyze, yeah, and select appropriate criteria. If we have independent samples, we should use to analyze the students' criteria. And students' criterion for independent samples is paired t-test if we if we have dependent samples. So, if we have not normal distribution law, this part no will be no. This will be yes. Sorry. What happened? If the hypothesis of normal distribution is not fulfilled, we describe our data by median and quartiles and interquartile range, yeah? And so, graphically represent them in the form of a box with a mass change, yeah? And after that, if we have two numbers or two groups or two samples, we should use the Mann-Whitney test. If we have independent samples, again, we must see dependence between samples. There is or there is no dependence. So if we have independent two samples, we should have Mann-Whitney test. If we have two dependent samples, we should put Wilcoxon. We should use Wilcoxon test. And for dependent samples is for analysis. And we have now considered situations where we have more than 3 samples because I said this is not a part of our course, and if we have no normal distribution law and we have more than 3 samples, more than 3 groups, we should use Kruskal-Wallis analysis, Kruskal-Wallis criterion, and post-hoc analysis. So today we finished our second part of medical statistics. On the next lecture, we will say about qualitative data. Today was quantitative data analysis. Next lecture will be about qualitative data analysis and correlation coefficient. So today I can say you thanks for the attention and goodbye.